Hi everyone, my name is Orlando Villegas Sanchez, and I will be presenting our work on holographic applications for Brownian particle confinement. This research was done here at the Physics Institute of an Autonomous University of San Luis Potosí with my advisor, Juan Rodrigo Vélez Cordero. And the main idea is simple. We use holograms to shape light into microscopic traps. You can think of them as tiny, invisible corals made of light that can hold particles floating in water. This lets us watch how just one or a few particles behave and interact. And how we create the hologram matters is the idea of this work. No? The computer algorithm we use actually change the forces the particle feel, and that change how they many behave. Okay, so first, so how do we actually create these traps? Let me walk you through our setup, which you can see the schematic in this figure. We start with a green laser, which provides the light of our tweezers. The beam is expanded to cover the most important component of our system, the spatial light modulator. You can think of the SLM as a high-definition programmable mirror. It's what allows us to digitally sculpt the light and shape it into the complex patterns we need for our traps, like lines or circles. Once the beam is shaped, it's relayed and focused down into our sample chamber with a high-power microscope objective. This tightly focused, sculpted light is what forms the optical trap that holds the particle. So, how does the optical trap actually work? At a basic level, we can explain it by considering two main forces that the light exerts on the particle, the scattering force and the gradient force. Okay? And now a key principle of this holographic method, and is we can generate what looks like the same trap in very different ways. This figure illustrates that concept perfectly. For example, if you look at these two computer-generated holograms, B or D, they are both designed to project a simple line. And as you can see the resulting image, C and E, they both do, but the important point for our method is understanding that even though the final shape is aligned in both cases, the underlying optical forces can be different. So how we choose to create the hologram is a fundamental part of our technique. In this work, we use basically two techniques, an iterative Fourier transform algorithm and lossless beam shaping. So let's move to the results. The first thing we used for our system was to characterize the particles themselves. If you take the figure 2, we show how can estimate the mass of an individual particle. We do this by trapping a single particle, like this image, in a line trap, and then carefully analyzing its vertical motion or its sedimentation behavior to gravity. Here we're showing the particle trajectories and his probability distribution at different age. And this main graph plots the dimensionless potential as a function of the particle's age. And by looking how the particle behaves at the bottom edge of the trap, which we call ceramin, we can determine its gravitational length, or LG, a value directly related to its mass. We perform this analysis for different particles to show the method works. A standard 3-micron particle shown in black, a similar one functionalized with hyaluronic acid in blue, and a smaller 1-micron particle in red. Essentially, this first result demonstrates that our holographic setup is sensitive enough to measure the effect of gravity on a single microscope particle. Okay, and so taking that one step further, we then asked, no, does the gravitational length we use measure change if we use a different hologram generation technique? And you can show the figure 3. This graph shows the effective gravitational length is directly dependent on the generation technique we use. Here we compare 3 different methods: a dynamic trap in green, a trap generated with the IFTA algorithm in red, and lossless beam shaping in blue. Each technique gives us a different value of LG. This is the first direct proof of our main idea. The algorithm used to create the trap change, the physical force that the particle experiences. This is a critical result because it shows that even for a simple trap, the choice of software can change the outcome of the experiment. And finally, to see the effect in other systems, we trapped a pair of particles inside a circular trap. And the result you can see in the figure 4. On the left, we created the trap using a simple drawn circle using the IFTA algorithm. And when we look at the distance between the 2 particles, we see a probability distribution with one clear peak at about 2 microns. This tells us the particles have one stable, preferred distance that they like to maintain. But now, look what happens on the right. When we switch the method to a super-Gaussian or lossless beam shaping, the interaction completely changes. This happens because the super-Gaussian method creates an additional potential in the center. So even though they are confined in circles of the same size, the central attraction completely changed the system behavior. What's interesting is that we can see the particles jump between T2's peaks or stable distance without spending much time in the middle. Okay, and this final result is the clearest demonstration of our central message. The algorithm used for hologram generation is not a minor detail. It's a powerful tool that can be used to fundamentally engineer and control particle interactions at the microscale. So, to conclude, our preliminary results or findings suggest that advanced methods like super-Gaussian or lossless beam shaping are minimally perturbative, meaning they are likely to better choice of these kinds of sensitive experiments. Okay, and thank you for your time.